is the C complex. That is the valence quark densities are small.
Sir, is there any probability to the C bar, T bar, the...
Yes, it depends on the accuracy with which you are doing. If you try to write down the density functions of the proton, then you have to have CB component also. But these are relevant only for high energy experiments. For the kind of experiment that we are talking about right now, it is not relevant. For example, when LHC we consider two protons collide, some process are initiated by the B partons inside a proton. So there, if you neglect the B, you will make a mistake. But it is not very relevant for the discussion related to Bjorken scaling and so on. Now, why this is so again will become clear. Unfortunately, I cannot do it right now. Then, what happens if you neglect these two? Then this ratio is 1. What happens if you neglect C? If you decided to work only with valence quarks, then you will not have these two terms. An experiment will tell you both the numerator and the denominator is 0, which means that you will get an indeterminate form. You cannot predict the ratio, whereas this ratio has been measured and it turns out to be 1. So this is one very good evidence in favor of the fact that the C quarks indeed exist inside the proton. But where did I take into account the fact that there are two valence quarks and two valence U quarks inside the proton and one valence D quark? That has not yet been taken into account. Therefore, when you try to fit the parton density functions or the quark density functions from data, you have to use some constraint equations also. This should be. Why? Because there may be many quarks, but there are two more valence quarks than the C quarks, and the number of U C quarks and the number of U bar C quarks are the same. Therefore, Ux minus U bar X cancel, and this should be 2. So when you fit the parton density functions from the data, you have to assume that this constraint should be satisfied. By the same token, now there is one d quark valence inside the proton. Therefore, this should be 1. And there is no strange valence quark. is really amazing how physics progress. When we talk about Higgs boson, we always remember that Higgs was first talked about theoretically, and much later it was discovered experimentally. The Higgs mechanism was proposed in 1964. Of course, we didn't see the Higgs of the model which Peter Higgs proposed. We didn't see that. But we saw something which is very similar to the Higgs in some sense. That is in the Glashow-Salam-Weinberg model, which was 67. And Higgs was discovered much. On the other hand, there are many examples in physics which was first discovered experimentally, and then the theory came. Okay? Rutherford scattering. It was discovered experimentally much before Bohr gave the quantum mechanical theory of the atom. So sometimes I find people uselessly debating that, oh, physics after all is an experimental subject. Or some theorists bragging that, oh, it is theory. We theorists, we say what is happening and then you see. Now both are rubbish. Because there are many pioneering examples in physics where the idea came from experiment. Similarly, there are many examples in physics where the idea came from theorists and then the experimentalists verified it. So the whole history of physics is full of this. So this bragging, both in the part of the experimentalists and the arrogance in the part of the theorists, both are completely useless. So you are young now, don't be biased. Now see, let me, sometimes, at this age you start to philosophize. So sometimes you ask people that, hey, what do you want to do? Well, sir, I will do string theory. Why? I like theory very much. It's no problem, but the trouble is the fellow is a MSc student and has no bloody idea about what string theory is. He has developed, probably by hearing to some bragging, some bragging theorists that, oh, string theory is the theory of everything. Now that is utter nonsense. You are an MSc student, there are a hell of a lot of exciting experiments going on, not only in particle physics. Particle physics, of course, it is the subject now, the LHC experiments. In neutrino physics, it is the experiment now. Hundreds and thousands of, this is why Sanjeev Agarwal, who is basically a phenomenologist, is so much interested in INO because he knows that he cannot survive without INO. So, this kind of thing is completely a false idea. And in particular, among the younger generation, if this idea goes that, oh, if I want to do something worthwhile, I must be a theorist. Now that's a rubbish. And unfortunately, the young fellow picked up that idea from some equally rubbish, arrogant seniors who said that if you don't do theory, you are in hell. It's completely rubbish. I mean, just keep an open mind, try to understand the experiment, try to understand the Higgs theory, try to understand the Higgs experiment also. See, yesterday I said it's needle in a haystack. And the subject, namely experimental high energy physics, which can pick up the needle from that haystack, must be equally brilliant. Peter Higgs was brilliant, Glashow-Salam-Weinberg was brilliant, but similar brilliance is there in the experimental side, who can really find a needle from a haystack, and systematically, not by accident. Alright, so now I will move to another tremendous experimental finding, which this already is one, Bjorken scaling. That was purely experimental thing, and then the pattern model came out of it. But now we will talk about another experiment which says that that we explain Bjorken's scaling and so on in terms of the parton density functions, identifying the partons with the thing. So let us consider the integral. Sorry for the notation, somehow the index P is there. So here it means indeed that U is the density of the U-type quarks inside a proton, but I have to write more. U bar, I wrote it twice. So what is xp? xp is the momentum fraction carried by a quark, and u is the probability that a u-type quark carries x fraction of proton momentum. Now if the quarks were the complete story, then this integral should give you what? Parton momentum multiplied by the probability that the parton carries x fraction of proton momentum. Well, if this P was not there, it would give 1. But if P is there, this is simply the total momentum of the proton. If the quark carries all of proton's momentum. If not, then it will be something like P minus P prime this represents the momentum of other particles in the very reasonable. If I can experimentally determine these two numbers, then I can determine whether P prime is 0 or not. Very reasonable. But then let me define, just to shorten the writing, let us define a quantity epsilon q, which is integral x dx dx plus u bar. That means the first term is epsilon u within the integral. Similarly, define epsilon d, which is simply in this expression I replace u by t. Then I get a result which is epsilon u plus epsilon d is equal to, I divide throughout by p, then this is equal to 1 minus p by p prime, all these ratios on epsilon prime. Okay. On the other hand,
so 1 minus p prime by p.
sorry?
1 minus p prime by p.
Oh yes, of course. Of course. So let me call it some epsilon. Now let me go through the formula of F2 here and F2 here, and that will give me oh, I must also tell it that here I assume that this is the so-called valence quark dominance. That is, we assume that the density of the valence quark is dominant. So U and D have some valence component in it. Therefore, their integral is large. S has only C, so its integral is small. So we have this relation to an approximation which is good. Then I go to the definition where I write F2 dpx dx integral, and this is equal to, by using the formula of